Okay, Mike, you made a central claim. And the central claim was that the machinery of the cell, you mentioned the bacterial flagellum, the eukaryotic cilium. In your writings, you've mentioned the blood clotting cascade were intelligently designed. We know that because these are all, by your definition, irreducibly complex systems. And another example of an irreducibly complex system is a mousetrap. As I understand the reasoning behind intelligent design, I want to ask you if I've got it right here. The evidence for design, of course, is at the bottom of this forceps statement. Let's start at the top. The cell contains biochemical machines in which if you lose a single component, it will abolish function, and that's your definition of irreducibly complex. I agree with you, by the way, that's correct, so I will stipulate number one is right. Number two, you said that any irreducibly complex structure that is missing a part is by definition non-functional, and that leaves natural selection with nothing to select for. You agree that's an important part of the reasoning?
No, the underlined part is your words, not mine. We've done this before, folks, Ken and I, a number of times, and he's going to say that there are other functions that can't. Somebody turned off my microphone. Oh no, that there are other functions that can be selected for, such as there are.
I just want to know if statement number two is a fair representation of your reasoning.
No, it's not.
Well, can you explain that? Because that's pretty much what you said. Any precursor to an irreducibly complex system that is missing a part is, by definition, non-functional. You said it.
Okay. Here's what I meant, and I think it's clear from my book. It's that the system itself has a function. The mousetrap, can catch mice. Okay. If you take apart the mousetrap, you can, hammer the mousetrap to your door and use it as a door knocker or something like that. So, but the point is that the system itself does not function. Yes, that's it.
Okay. Then you say, therefore, since there's no function, irreducibly complex structures cannot be produced by natural selection, and therefore, they must be the product of design, since natural selection is the only alternative. Have I got it right?
Well, again, not quite. I don't mean to quibble with you, but I do not say that just because they can't be produced by natural selection, they're products of intelligent design. I try to go through the logic in my own non-philosopher way towards the end of the book about how we come to a conclusion of design and try to show that the systems meet that.
Okay, what you said, of course, is that this, again, your words again. If a biological system cannot be produced gradually, it has to arise an integrated unit in one fell swoop for natural selection to have anything to act upon. That's on the basis of which I put those four together.
Yes, and later, in a later chapter, if you remember, I talked about Stuart Kaufman's work where he talks about complexity theory, which he thinks can produce systems in one fell swoop, but not by intelligent design. Lynn Margulis's ideas of symbiosis, which could produce new functions, but not by intelligent design. So I was just making the more limited point that you would have to get all the parts together for something to act on. And it's only later on, I think in chapter 9 or so, that I argued for intelligent design.
My point is that statement number two is really the core of the argument. And what I want to do is move ahead and examine that. And again, this concept of irreducible complexity, here is your definition of it again. Several closely matched parts in order to function. The removal of one of the components causes the system to stop functioning. It's very, very clear. Now, the poster child for irreducible complexity clearly is the bacterial flagellum. Both of you mentioned it. Bill has it on the cover of his books. My friend David DeRosier has written, it almost resembles a machine designed by a human, and about 50 genes are particular to the flagellum and its chemosensory machinery. And it is an extraordinary structure. I agree with you completely on that, and I think so do all biologists who have looked at it. However, here's the point. Let's suppose we test your idea of irreducible complexity. We start with a 50-part bacterium, 50-part bacterial flagellum. We take away 40 of the parts. And what that does is it leaves just 10 parts behind. And the 10 are shown right there in this little structure. Those 10 parts ought to be non-functional by your definition of irreducible complexity. But it turns out, as you know, that they are not. Those 10 parts turn out to form the type 3 secretory system. And again, there's your statement. Any precursor to an IC system that's missing a part is by definition non-functional.
There's a question.
Here is a point that is by definition non-functional. Doesn't that mean that the idea of irreducible complexity is wrong?
Well, no. for the same reason that I was trying to say before, the function of the system is to be a rotary whip and to propel the bacterium or to push liquid over top of it. This does not have that function.
It's a different one.
That's correct. It does. Hold on a second, though. Let me say a couple of things before we proceed. First of all, it doesn't have the same proteins. It has proteins which are homologous to some of the proteins.
Strongly homologous.
That's correct. Okay. Well, homologous. And again, with the results from that paper that I cited, it's no longer something safe to say that we can be sure that we started from this homologue, went to this one by a Darwinian process. And that's one thing.
I didn't raise the issue of process, Mike. All I said was, here's a subset of the parts, they work.
Well, yeah, the problem comes in when you say a subset of the parts, because the amino acid sequences of these things are different. And not only that...
Just different enough to tell them apart.
Not only that, but it also has other proteins which work with the type 3 secretory system. So this does not form a complete system. A second thing, point which might be relevant for the audience to consider, is that I think where Ken's going with this is he's going to say, well, maybe we could start out with something like this.
No, that's not where I'm going.
Okay, well, let me say it anyway. Start with something
I didn't realize you got to make another statement. I want to question you. Please don't answer a question I'm not going to ask.
Go ahead.
Okay, so the point stands that a subset of these proteins is functional in a different context. And that's the bacterial flagellum. Let's look at a couple of the other guys. Let's look at the clotting pathway. This is the way in which blood clots. You call this the Rube Goldberg in the blood. Great stuff. And the clotting pathway is extremely complex. It produces a clot around the red blood cell. And what you wrote is, in your book, is that none of the cascade proteins, these proteins, are used for anything except controlling the formation of the clot. That's very clear. Yet, in the absence of any of the components, blood does not clot and the system fails. Again, your words. Now, here's the hard part for me. Remember, you said in the absence of any of the components, blood does not clot and the system fails. One of those components that you've talked about is called factor 12, or Hagemann factor. And you'd think if we take it away, the system should fail. So there shouldn't be any living organisms that are missing Hagemann factor. But it turns out, lo and behold, that there are some organisms that are missing Hagemann factor. I've crossed them off up there. And those organisms turn out to be dolphins and porpoises. They don't have it. I assume that statement, therefore, is incorrect and has to be changed?
Well, first of all, let me express my condolences for the dolphins.
I assure you, you don't have to do condolences. They do fine.
Okay.
That's
well,
the point.
It's
the theory of irreducible complexity that needs condolences at this point, because that's what's happening.
Well, if you read my book a little more closely, you'll see that I talk about both the intrinsic and extrinsic pathway. I say that they can use both of them. And you'll see that when I talk about irreducible complexity, I say the details of the pathway beyond Christmas factor and so on are rather vague. So so I said we'll confine my argument to those. But nonetheless...
Yeah, but your own words are up here, and you point out Hagemann factor, factor 12, and so forth. So they're part of that system.
Well, nonetheless, let me point out that if you do delete prothrombin, if you delete tissue factor...
Well, I'm asking about Hagemann factor.
I'm sorry?
I'm not deleting those. My question is straightforward. You said you couldn't delete them. Nature's done the experiment. It deleted them. Doesn't that disprove the hypothesis? And you're talking about deleting other ones.
You're right. There is redundant components in the blood clotting system.
So it's not irreducibly complex.
In the same sense that a rat trap is not. That's correct.
Okay. So again, your use of that as an irreducible complex system breaks down upon inspection. Now let's look at the cilia, because you said how beautiful this structure is. And let's take away not one part, not two, not three, not four. Let's take away 5. And the parts that I've just X'd out here. And that would include the central doublet, the outer dining arms, the cross links, and a whole series of other components. And that's what we'd be left with. And once again, nature has done the experiment. Your system, you call it irreducibly complex. Any irreducibly complex system missing a part is by definition non-functional. We take away the parts, and does it work? Well, that's the cross-section of the flagellum of an eel sperm. And whatever else one thinks about eels, and some people in the audience may have strong feelings about them, eel sperm is fully functional because its job is to make baby eels, and it's good at it. What does one do when it was told a system is irreducibly complex, finds systems missing parts, and they're still working?
Well, one reads a little more closely, and one sees that I said in my book that it was required to have microtubules, linkers, and motor proteins.
Indeed.
And indeed, I pictured, and as a matter of fact, I showed the picture from my book here, that in fact all of those structures have those. And the experiment has been done. If
okay, so actually irreducible complex system is smaller than this. It's smaller core, right?
And if you take away one of those components, then the system fails.
Okay, very good. Now, one of the things I like about your ideas is they provided us a test, an empirical test, for the idea of intelligent design. And once again, I maintain, even though I think both you and Bill have self-consciously tried to sort of misstate irreducible complexity to get out of it, and that is that the parts of these systems ought to be useless on their own because, as you put them, natural selection would have no way to make them, and evolution basically predicts that the parts do other jobs.
Well, can I just stop you there a second?
Yeah.
First of all, I wish you wouldn't say that we are intentionally trying to misrepresent something, because we're not. The second is that I never said that they are useless on their own. As a matter of fact, if you read closely in my book, I talk about the microtubules being used in other things, dyning motor proteins being used in other things, and so on. And I clearly say that, just as I said here tonight, even though they can be used for other things, the problem of irreducibility remains.
Yeah, but you also said that natural selection has no way to make them. And the major components of the cilium include proteins like tubulin, dynein, and actin, and these have distinct functions in the cell that are unrelated to ciliary motion. So what can one make of the main argument, which is the parts of an irreducibly complex structure have no function on their own? And remember, your statement, any precursor that's missing a part is by definition non-functional, but it turns out that these individual parts are fully functional elsewhere in the cell, and there's a selectable function for each of them, and doesn't that mean the argument is wrong?
Well, no. I think, perhaps, something in my speech isn't getting through, but I'll just appeal to the audience. I did not say they have to have no function whatsoever.
By definition, non-functional.
I said that the function of the system is missing. I'm happy to admit that similar proteins can have other functions in the cell, but the system loses its function.
Yeah, your words, I think, speak for themselves. Okay,
I don't know.
The way I see it, Mike, is that the reasoning behind intelligent design is contained in this slide, which is the one that we talked about before. And point number 2 is the inference that we can really judge on an empirical basis. And what I've just shown in those 3 systems, which are your systems, is that that vanishes upon inspection because those parts are useful, and therefore the 2 conclusions vanish as well. But let me go to the mousetrap, since we brought it up, and I have a mousetrap here for anyone who doesn't remember what they look like. They've got 5 parts. Good for you. Excellent. Excellent. The mousetrap, if you have stock in a mousetrap company, Behe and I are responsible for your rise in stock. Now, some of you may have noticed that I'm wearing a mousetrap tie clasp. This is a mousetrap from which I have removed 2 parts. Just as Mike said, doesn't work as a mousetrap, works fine as a tie clasp. Hang on. Okay, sorry, I didn't realize who I was talking to. Sorry, Ginny. Okay. 2 parts of the mousetrap do very well as a keychain. I'll be selling these as souvenirs later on. And 1 part for the mousetrap is quite good as a toothpick. And the point is that the parts of an irreducibly complex machine are fully functional for different purposes. And here's my closing question, Mike. You've brought us 4 systems as examples of irreducible complexity. And what we've seen as we've gone back and forth is that every one of those systems breaks down upon inspections. The type 3 secretory system still works, although it's lost 75% of its proteins. The clotting cascade still functional despite losing a protein. Smaller parts of the mousetrap still work. Tubulin and dynein still function outside the cilium. If ever any idea was subject to an empirical test as easily as the idea of irreducible complexity, this is it. And it looks to me and to anyone who else is looking, this idea has failed in every single test.
Mike, would you like to take a minute to respond?
Yes, thank you. I appreciate your point of view, but I disagree with you. Your use of the mousetrap is very interesting. I discussed that on that website that I flashed up there. Ken has posted some stuff on his website. Anybody who wants a full discussion that can go beyond the time limits we have should look those things up. But as Bill said, in these mousetrap things that Ken does, you know, he's using his intelligence to rearrange parts. Furthermore, you know, I ask members
no parts
of
rearranged.
It's my turn. I ask people, men in the audience who have tie clips, to take a look at them. Do they look anything like that? If so, I'm sure you're not here with a girlfriend or your wife. And that's because tie clips would be formed more practically. Ken is using that because he wants to go toward an end. Here is my keychain. It doesn't look like the mousetrap one. He only selected the mousetrap keychain because he wants to think you can get to a mousetrap by a random process.
Thank you. Now there will be 5 minutes of question by Rob Pennock for Michael Behe.
Can I use one of your slides, Ken? Do you have a definition of irreducible complexity up there in one of them?
I'm starting the
I didn't have
clock.
much success early on. I really want to be an ID theorist, and I wanted to know how to do it. And I couldn't quite get too many straight answers from Professor Dembski, but I'm going to try once again now with the question of irreducible complexity. This is actually relevant, and let me just connect it to the previous point. For Professor Dembski's specified complexity and his explanatory filter, he cites irreducible complexity as a specific instance, a case of specified complexity. So this is important because it links the two talks. If the explanatory filter is as perfect as we've heard, we should be able to have a test case here to see of it. If we can find a case where irreducible complexity fails, then it seems as though we have immediately a case of specified complexity failing. So your judgment on whether irreducible complexity stood or failed actually pertains also as well to the previous talk. Okay.
Your question,
so
please.
Here's the question then. How can we really tell? I mean, the thing that's gone on here is a back and forth about, is this something that counts or is this something that doesn't count? Does this specific system fit or does the specific system not fit? And you're both disagreeing about what does and doesn't. Let me just ask if this would count for you as a sufficient identification of such a system. Okay? I'm going to try to give you your strongest position, and let me just see if you agree with this. If we could find a case where we perform a bunch of knockout experiments, we identify something, whether it's the flagellum or some protein system, and we're asking what are the parts that count. Okay? Does this part count or not? Would you be satisfied if we performed a series of knockout experiments and just said, here are all the components such that if we knock these things out and every one of them gets knocked out, that will just call the irreducibly complex system. So notice in the mousetrap case, you don't include the cheese. Right? Someone might have thought you need to have the cheese, but no, you don't include the cheese in yours. Okay? So there are a bunch of things, we call them redundancies. Right? So would you be satisfied if we just left those out and said, knockout experiments will tell us what counts as the system?
Well, I'd say it's a good place to start, but I would reserve judgment. I'd like to see exactly what the proteins are doing.
So if we have a case, I mean, because I would have thought you would have been happy with this. I want to get something that you'll be happy with, because I want to be happy with this too, right? I want to know, because I've never been convinced that your examples are actually even fulfilling your own definition. Okay, so I want to find out if I have all these parts here. There are 10 parts, okay, and I knock out 2 of them. They don't actually wind up losing the function. The function's still there. You'd say, well, those really weren't part of the minimal system. Okay, you want to find the minimal system. Okay, so if I knock this one out, then it fails. I knock this one out. All the other ones, if I knock out, those fail. Then we'd have to say that's a minimal system. That's an irreducibly complex system.
Well, again,
just by knockout experiments.
I know you're a philosophy professor, so I'm sure you like distinctions. I think that's a good place to start, but in order to understand the system, you have to know what's going on, what's working on what, what's doing what to whom. And without a further description of the system, I'm smelling a trap that you're trying to lead me into.
A mousetrap, perhaps.
Mousetrap.
This is the problem, and it looked as though you had a definition here where all we had to do was see, right, order to function, removal of one of the components effectively causes the system to stop functioning. I'm going to grant you a single function. I'm not even at this point going to talk about different functionals. I just want to know, how do I know that I have one? Okay? And it seems to me as though if I perform a knockout experiment and say, here, I'll just define it, I'm going to give you your definition, why wouldn't that satisfy you?
Well, because
I've done everything you wanted, Bill.
If you read in my book, I say that in order to decide if something is irreducibly complex, you have to see what the parts of the system are, how they interact.
How do we tell?
And see, well, we do biochemical investigations.
Knockout experiments.
That's one way.
Okay, so that'll work. That's a sufficient way?
I keep saying you keep not hearing. That's one way, but you have to know more.
Well, we're not going to hear anymore because we've just sort of blown all of our time.
I was really hoping I'd be able to become one tonight, but I'm afraid I'm not yet able to become an
somehow I don't believe you.
Okay. We have a short amount of time for questions from the audience. Not a whole lot of time, I'm afraid, but a little bit of time. This gentleman over here in the corner, speak very loudly, please.
You gentlemen have been discussing the details of intricate biology. I'm asking a question about some giant things in the universe. How does a believer in intelligent design explain the questionable intelligence behind a design which periodically blasts the Earth with apparent random space rocks, thereby destroying much of what has been previously designed?
Is that for me?
I think it's up for grabs.
Well, that's an excellent question. I don't know. It's certainly, I think that in the universe there is not only design, there is natural law and there is randomness and so on. And so perhaps this is part of the design and it doesn't look so good to us, but maybe it's just the outplaying of natural law or something. But what I don't think you can say is that the Earth has been struck in the past with meteors, therefore the bacterial flagellum was produced by Darwinian evolution. I do not think that follows.
Another question. It is hard to see here. This man in the front. And to whom are you directing the question? Okay.
Thanks very much. Actually, I think a strong point of design, kind of counterintuitively to many people, is that it's easily falsified. Ken has been trying to falsify it. He's a number of examples that he likes. He thinks if his examples are correct, it would be falsified. A number of other scientists who are no fans of intelligent design have pointed to experiments in the literature and said that this falsifies some of the claims of irreducible complexity and so on. If a scientist went into the laboratory and grew a bacterial culture for a long time, say, tens of thousands of generations, and saw that some new irreducibly complex system was produced, then my claims would be gone. It's straightforwardly falsifiable. If we can show that new irreducibly complex systems can be observed arising in the laboratory, then there is no need to say that it required intelligence to do that. Now, kind of as a side thing, let's flip the tables and say, how could we falsify the claim that Darwinian processes produce the bacterial flagellum? Suppose you went into the lab and grew a bug for a long time and asked yourself, did it produce something like a flagellum? And it turns out it didn't. Would Darwinists think that their theory had been falsified? I doubt it. They would say that there wasn't enough time, you started with the wrong bacterial species, and a lot of other reasons. Now, those may or may not be valid, but the point is that intelligent design is pretty straightforwardly falsifiable in my view, but Darwinian evolution is not.
Ken?
I'll respond to that very quickly. The first point is the idea of an intelligent designer is inherently non-falsifiable since it's an agency acting outside nature, and we only falsify things by natural causes. When Mike says, I've been trying to falsify intelligent design, here's what he really means. He says that we know intelligent design, there's evidence for design, and that evidence is on the basis of the existence of irreducibly complex systems whose parts could not have been formed by Darwinian natural selection because they are in themselves useless. That is the argument that I have attacked, and I think I have falsified, and other people have falsified as well. Dr. Behe, for example, quoted a retired biochemistry professor, a gentleman whom I actually know, Frank Harold from the University of Colorado Medical Center, as saying we don't have any examples of the evolution of complex biochemical systems, and that was taken as authority. Now, Mike should know that 2 years before Harold published his book, I listed a series of examples of papers showing the evolution of complex biochemical systems. I can cite 2 of them that describe the evolution of the components of the Krebs cycle, which is complex, biochemical, and real. I can cite another one that talks about the evolution by, quote, a step-by-step Darwinian process of the genetic code and the coding machinery of the cell. And lastly, Shelley Copley, in the year 2000, published a paper describing the evolution in the last 65 years of a new biochemical pathway that detoxifies the pesticide pentachlorophenol, which was first synthesized in 1935. There are papers in the literature, despite what Dr. Behe said, and these papers falsify his claims.
Can I just briefly mention? Well, Ken and I disagree on this, and please go to our websites for details. The question I have is, it's not just me that says it. Do you think that Dr. Harold didn't read these papers or didn't read your book or something? What's with him?
Well, I don't have such a strong opinion of myself to say for sure that Frank Harold read my book, but I do think that he's making a generalization, which is that most complex biochemical systems have not been explained by Darwinian natural selection. That generalization is correct. Remember, I said most. But the point is, to falsify your contention, you only need one. And I wouldn't be at all surprised, given the thousands of papers in the literature and Frank Harold's own particular research interest, that he might have missed these 4 or 5 that I've cited.
And Stuart Kaufman did too, I guess.
No, Stuart Kaufman has come out very strongly as saying that when he talks about natural selection, he's talking about fully naturalistic mechanisms that promote the development of the structures and the biochemical pathways that you folks attribute to design. And Kaufman has actually published, I thought it was a rather pointed press release in response to the Discovery Institute citing him as a scientist who cites non-Darwinian mechanisms, saying, wait a minute, you guys, the mechanisms I'm talking about are fully containable within the Darwinian understanding of things, just they don't relate directly to natural selection.
Just want to say something with regard to natural selection. Natural selection is a trial and error mechanism, and it turns out that there are different contexts in which we see evolution and where natural selection just doesn't do the job. Where intelligent design really comes from is not looking at evolution in this mechanistic way, but thinking of it in terms of technological evolution. What you find within the technological context, it turns out that there were some Russian patent engineers that had nothing better to do with their time than to look at, this is in the former Soviet Union, look at patterns of technological evolution, see how patents evolved. And what they found was that there were 2 types of problems. There were routine problems, which you could solve by just tinkering with existing systems. And that's basically, from our perspective, Mike's and mine, that's what natural selection does. But there are also inventive problems where you need a sudden insight, an intuitive leap to try to make sense out of, to solve a problem, to get a new fundamental structure. And that's what we're seeing with systems like the bacterial flagellum, that they are types of systems that are intrinsically or inherently beyond the scope of mechanisms like Ken Miller points to. And we have there are past cases where you have theories of transformation where the resources you give yourself to try to account for the transformation are inadequate. Alchemy is a failed science. You cannot transform lead into gold given the limited resources that the alchemists had. And that's what we want to say, that those resources that the Darwinist has given him or herself are inadequate. Now that's a legitimate question. You know, we may be wrong, but that's a question that should be put on the table. And there are, if you look at technological evolution, there are different types of problems. Some problems which are not amenable to trial and error or these sorts of natural selection mechanisms.
Just to try to connect these two things here, could you tell, I mean, is it true you agree that the bacterial flagellum, in case of irreducible complexity, is a case of specified complexity?
In Chapter 5 of my newest book, No Free Lunch, I lay out some techniques for assessing probabilities for systems like that. And the sorts of probabilities I'm calculating are indicating that indeed the bacterial flagellum is a system that exhibits specified complexity.
Okay, so yes for that one. Is it the case now, you've made a distinction between actual complex specified information, actual design, and apparent. Can you tell the difference looking at this, whether this is a case of actual or apparent? And how do you do that?
The whole point with apparent, it's what I was talking about in my paper today. It's that specified complexity, what you're trying to do is get at, you're trying to figure out the relevant mechanisms that we know with our best science, do they account for what we're seeing? And according to those mechanisms, the probabilities end up being extremely low. Now, we may have missed some mechanism. There may be some mechanism that's operating in a way we don't know. Okay, now this is where the design critic will want to say, well, it's just an argument from ignorance. We, on the other hand, will want to say, no, you've exhausted the resources of these material mechanisms. Now, how can we do that? I mean, if it's just, you know, well, there's always a possible mechanism out there. Well, I think one of the things which gives traction to design is when you start looking at systems like systems of polymers, where the geometry of these systems is telling us, look, as far as the physical laws are concerned, there's total interchangeability. So what is it that's singling out certain collections of polymers that have a certain function? That's where I think we get where it's not just an argument from ignorance, where there's good reason to think that, in fact, these systems are beyond the remit of material mechanisms.
Gentlemen,
So
we have come to the end of our time. Would you like, we haven't talked about this previously, if you would like, you could each take 1 minute for final comments. These are not questions for one another, but if you have any final profound thoughts to give to us, and I would like to start at the far end of the table from me with Ken and work our way up here so that the two proponents of intelligent design do indeed get the last word. Would you like to do that? You don't have to take your minute. These people are probably awfully, your ischial callosities are probably, it's too bad they didn't stay in the hominid line here because you're probably very tired of sitting, but would you each like to take a minute? Anthropology, what can I say? Okay, Ken, you may have 1 minute.
That was a very disruptive introduction.
You have 1 minute.
We all need a minute to compose ourselves. I'll answer as quickly as I can. I think intelligent design theory, as has been presently put forward, fails the empirical scientific test, and it fails it on every score. Every single prediction that has been made by Mike, for example, with regard to biochemical systems, breaks down upon inspection and requires a constant retreat from saying, oh, the system is smaller, and oh, I meant it applied to the whole system, not to individual functions, and so forth and so on. And that's one of the reasons why this idea has attracted very little, if any, scientific support. And I'd also like to point out to Professor Dembski that there is a way to test his ideas, and it would be a very interesting test. And that is to take the very experiment from the PNAS paper that I cited that talked about the increase in fitness and the number of gene duplications and amplifications and deletions that produce that, and put that into his calculations based on the explanatory filter to see if it is predicted as being impossible. If his technique says that what happened under the eyes of an investigator is impossible, it means that his technique is wrong. And I'd be interested in trying to make that test.
I'd be
Okay, the
interested in
next
collaborating
one's-
with you on it.
Rob, would you like to take 1 minute?
Sure. This is something where the test of a scientific theory in part is, can you tell what it is? Can you be specific? This is the heart of Professor Dembski's view, specified complexity, being precise, being specific. Try as I might, I can't get a specific answer to some specific things. Here's the issue, though, about a test case. If specified complexity is the way to find this out, then we should be able to identify, here is a case that has it. Right? If irreducible complexity is meant to be an instance of that, we should be able to find a case that has it. Until we can identify what does, what doesn't, we're not in any way able to test this. In Professor Dembski's own definition of how the explanatory filter works, the options that are swept clean, he says we sweep the field clean of probabilities. He says we do this relative to the set, I'll quote here, relative to the set of all chance hypotheses in the light of our context of inquiry. That's to say, the ones we've thought of.
Thank you. And Mike, would you like to have a comment?
Thanks. Well, I of course, as you might guess, I disagree with Ken. I think irreducible complexity and the tenets of intelligent design are doing well. But here I want to say, this is a lot of fun. I really enjoy trying to get these ideas out and discussed in public. But it really matters little what we four here are saying, because it's the progress of science that's going to settle this once and for all. And as I said, 50 years ago, it was a lot easier to believe Darwinian evolution is true. In the next 20 years, we'll learn a lot more about the cell, and I'm really rather confident that design will be vindicated.
Thank you, and thank you for being short.
Hey.
Yes.
Look, Let's move on.
Heightest you.
For which I apologize. Thank you.
Yeah.
Please.
I'd just like to make a comment about the nature of science. And I would say that the nature of science is not fixed in stone. Science has been around for over 2,000 years. Science used to be called natural philosophy. And I think what we're seeing here is really we're coming to terms with what happened, not even so much with Darwin, but with what happened with the rise of modern science. The rise of modern science, it was a mechanistic science. You had Newton, Copernicus, Galileo. They were looking at a world of particles in motion, trying to describe dynamics of motion for these systems. It was not a world on which you could easily graft design, even though these originators of modern science were theists. And so this mechanical universe led to actually the dissolution of design, because you couldn't really make sense out of the particles in motion do their own moving, they can do their own designing. And I think what we're now finding is that information theory, design is coming in a new way. And it's, that's
you.
the end. So there are new possibilities for science here.
I had a request, a good request from an audience member. Would each of you gentlemen get out your pens and pencils, boys and girls. If you want to take down the websites, they will recite them for you. Ken, slowly recite your website and work your way up the table.
Yeah, I'm going to recite it in a real simple way. I teach at Brown University. So you go to brown.edu. Brown.edu, it's an educational institution. Then I'm in the Department of Biology. So you go to academic departments, look for biology, look for the list of faculty. My name is Miller. You'll find my website with my smiling face on it, and there's a little link that says evolution, and that's where you can go to. So I'm Miller, I'm in biology, I'm at brown.edu.
You want to give your website?
For me, I'm at Michigan State University, and the easiest thing to do actually is just to open up Google and type in a name, Robert T. Pennock homepage, or just Robert T. Pennock, and no doubt you will almost immediately find my direct homepage there.
For me, I really don't have a web page, so why don't you go to that address I put up on the screen, is www.crsc.org. crsc.org, crsc.org.
Let me direct you to the International Society for Complexity, Information, and Design. So that's www.iscid.org. And I'd love if you'd play with www.iscid.org and play with that MESA program. See if it doesn't undermine your confidence in the Darwinian mechanism.
And for more analyses of all of this, which as moderator I'm not going to mention tonight, you can go to my webpage, which is ncseweb.org. Ladies and gentlemen, you've been a wonderful audience. It's been a wonderful panel. Thank you.